Good.
Okay, hello everyone, and again, welcome to the second session of track number 2 for the Hot Interconnect tutorials. Please allow me to introduce our speakers for the next session. We're going to be hearing about OFI Libfabric. Our first author is Rajalaxmi Angadi. She is a middleware engineer manager at Intel Corporation and leads the Libfabric software productization team. She has over 17 years of industry experience in various capacities, ranging from design and development to management. She's been heavily involved in developing schemas and mockups for SNIA Swordfish in the Scalable Storage Management Technical Working Group. She's also co-authored multiple technical proposals and contributed to the NVMe Consortium. She's a key contributor to the Distributed Endpoint Manager, an open source tool for managing NVMe over Fabric resources. She's also a core team member of the Technical Women at Intel Network cross-site committee, focusing on the EMEA region. Prior to Intel, Rajalaxmi has worked with a stealth mode startup, Semantic Software, Computational Research Lab, HPE, and Flextronics. She holds a master's in information technology and management and a bachelor's in computer science and engineering. Second, we have Juee Himalbhai Desai. She's a middleware development engineer at Intel Corporation, working under Rajalaxmi to support Libfabric software productization. She has 2.5 years of industry experience working in computer networking, and she's been with Intel developing and testing Libfabric components for the past 10 months. Prior to Intel, she was at Pluribus Networks, working on physical layer technologies. She holds an MS in electrical engineering from USC and a BE in electronics and communication. So again, I'll remind you all that we plan to have the Slack channel open for questions. And I believe, Rajalaxmi, our plan is to have one person present and the other field questions as they come in, if possible. And if not, we can take time at the end for questions and, of course, respond to Slack, throughout the rest of the day, and I think even beyond. Is that correct, Rajalaxmi?
Yeah.
Great. So feel free to take it away when you're ready.
Yeah. Okay. I think. So, can you switch back to the presentation, Juee?
Yeah, we see a Visual Studio window, I believe.
Juee, I think you have the control. Can you switch back to the presentation?
Am I not sharing the presentation?
Yeah, can you switch back to the presentation, Juee?
We see a Visual Studio window for the example,
Yeah,
I believe.
yeah.
Okay, 1 second.
Sorry about that.
Yeah. Okay, are you seeing the presentation now?
Yeah.
That's good.
Yeah. Okay. So, yeah. Hello all, and welcome to the Hot Interconnect Conference 2022. And today we are going to be presenting OFI Libfabric tutorial. Thanks, David, for nice introduction. So this is Rajalaxmi, and I have Juee along with me to present the tutorial. So the agenda for today is we'll go through the conceptual outline of Libfabric first. Then we will do a little bit of architectural outline of Libfabric. We'll not go into greater detail over there, but we'll have it as a groundwork for us to go into the APIs, and then followed by few messaging applications. We will dive into various parameters that Juee is going to explain, and then we will go into actual examples of the API, of applications that will make use of Libfabric APIs. Like we'll see tag matching application, we'll see RMA, or we'll also see about memory registration capabilities. So what is OFI Libfabric? So OFI and Libfabric are sometimes used interchangeably. So it's basically a framework that focuses on exporting Fabric's communication services to the applications. You can see on the diagram on the right side, we have at the bottom, we have hardware, which will have, which could be various network interfaces. There are corresponding drivers, and then we can see the Libfabric that's sitting right in between the application middleware and these providers. So Libfabric provides that tight semantic map between this application and the underlying Fabric services. So Libfabric is also designed for the performance and scalability requirements of these applications that are running in the tightly coupled network environment. For example, there could be different kind of applications that are on the top, and Libfabric provides the interface to those applications. And at the bottom, there could be different networking interfaces provided by different vendors, and they could have different providers, and then it provides that that mapping, and it also exposes those additional features to the application middleware so that they can be easily designed. The key components of OFI are these application interfaces, like I said, that are facing towards the application middleware on the top. There are provider libraries that will cater to various providers at the bottom, and there are some kernel services and daemons. And along with these, we have test applications that are used to test various features of Libfabric itself. And Libfabric is supported on all major Linux distribution. However, the validation is limited to 2 or 3 releases of Red Hat and SLES. Now let us dive into a little bit of architectural outline of Libfabric. The diagram on the side, you can see that it expands the view of the Libfabric itself. On the top, we see there are different applications like MPI, SHMEM, PGAS, and at the bottom, we can see there are the software that's NIC specific. So OFI is divided into 2 major components. One is the Libfabric itself, and there is the provider layer. So the Libfabric caters to these major 4 verticals of services, like you see here. There are control services, which you can see here, which is used by the applications to discover information about the types of communication services that are available into the system. Through these services, the applications can find out what kind of services they are dealing with. For example, the applications can check what best RMA capabilities are present and what other features are available. For example, FI Get Info is one of the APIs that caters to these control interface services. These are basically all different type of interfaces, API interfaces. Next, we have communication interface. This is used to establish connection between the endpoints, and it does that with various connection management APIs. Like we can have connect, bind, listen, accept. Later in the examples, you will see what are these different connection management APIs. So along with the, it also caters with for the unconnected connections and the connection-oriented services. It also addresses, it also has these something called as address vectors that abstracts the fabrics, and it also abstracts the fabric addressing associated with each of these fabrics. By also sharing the addresses, it can also do the address resolution. All these kind of APIs are bucketed into these communication interfaces. Next, we have completion services. So completions so whenever any message is sent or received, we also need to report the completion, right? So these are done through completion queues, and they provide details about the operations that that got completed. So completions could be detailed oriented, or they could be a lightweight completion. So depending on what the applications or what is the requirement of the top level application, they can be just a simple status completion message, or they could be just the counter service that could just increment a counter whenever the completion is done. So it could be a lightweight completion, or it could be a heavyweight completion. Next, we have data transfer services. So the data transfer services are the ones that are actually used for sending and receiving the data, along with the message boundaries that are maintained. So we have the 4 types here. Message queues we can consider like they are FIFO, and there is tag matching, and there is RMA. Tag matching deals with the messages that have specific tags, and out of order messages can be identified with the tags. RMA is nothing but the remote memory access, wherein there is memory allocated on both sides that the client or the server can access. So it as the name stands, it's the remote memory access, right? So, and then there are atomic operations that are similar to RMA, but there we can actually allow manipulation of the memory. So later in the slides, Juee is going to explain examples of tag matching, RMA, and message queues. And she will also explain various APIs which are used for control services, like, for example, FI get info. She'll talk about the communication interfaces, like setting up what APIs are used for setting up these communication between nodes, and then how completions are handled through the completion queues. So going forward, this is how the APIs are grouped. So the color scheme on this slide kind of matches with the color scheme on the previous one. So for example, the generic API here is nothing but the control service interface, and we have FI get info over there. And all the green ones show the communication services. Like I spoke, they are used for managing the connection, right? So we have address vector type of connection management. We have endpoint management through FI passive endpoint and FI endpoint. And we also can see there are like set of completion services interfaces through completion queues, APIs like FI CQ open, FI CQ read. And there are like completion counter APIs with like FI counter open and FI counter read, etc. So I'll let Juee take over from here, and she can go through all of these APIs, and she will also go through some actual examples, and she'll show the live execution of these examples. Over to you, Juee. Thanks.
Thank you, Rajalaxmi. So all of the Libfabric services that we saw in the architecture can be segregated into these objects shown over here. There is a relationship between these objects, which we will understand in more depth later on. This is just a high-level view of relationship between all the objects that create the base of Libfabric. So fabric and domain are 2 most important parts to Libfabric. Fabric might be a single network subnet or a cluster, and a domain represents a logical connection into a fabric. The only API that is not having any relationship with others is the generic API, which can also be categorized as a control service API. And we will start with the FI get info call. So the FI get info call is one of the first calls that most applications will invoke It is designed to be easy to use for simple applications, but it is also extensible enough to configure a network for optimal performance. So FI Get Info call in general will provide information about all the resources and services present in the fabric. The main purpose of this call is to allow an application to specify which features they require of the network through the node service and hints parameters. So node is commonly used to provide a network address such as an IP address. Service is basically a port, so it's a transport address such as a TCP port number. The hints parameter is the key for requesting fabric services. The FI info structure contains several data fields plus pointers to a wide variety of attributes like transmit attributes, receive attributes, endpoint attributes, to name a few. In case the caller specifies null for node service and hints, FI Get Info will return information about all providers that are available and their optimal usage models. So this is another purpose of the FI Get Info call. Now, in case if no matching information is available, info will be set to null and the call will fail. So the top level object that applications open is the fabric identifier. The fabric can mostly be viewed as a container object by applications, though it does identify which provider these applications use. It is important to note that a fabric needs to be opened before allocating any other network resources to the application. So opening a fabric using FI Fabric is usually a straightforward call after calling FI Get Info. And once a fabric is opened, all the network ports on that system that can communicate with each other through their attached networks belong to that same fabric. The fabric attributes can be directly accessed from FI info struct obtained from FI Get Info call, and the newly opened fabric is returned through the fabric parameter present in the FI fabric attribute structure. So domains usually map to a specific local network interface adapter. From the viewpoint of the application, a domain identifies a set of resources that may be used together. And a single fabric can have multiple domains. So a domain creates boundary for associating resources like endpoints and completion services together. It can also be said that a domain defines the relationship between data transfer services or endpoints and completion services or completion queues and counters. Many of the domain attributes describe that relationship and its impact to the application. So FI domain is a simple call that opens a new domain, and the FI info struct obtained from FI Get Info can be directly passed here. The next call is FI domain bind, which is used to bind completion services like event queues to the domain that we just created. And we will know more about event queues later on. So endpoints are conceptually similar to a connected TCP or the UDP socket. So endpoints can be associated with the transport layer, and they can also be called as communication portals. Endpoints are mainly of two types, so passive and active, and there are different calls to open these two endpoints. So passive endpoints are associated with the fabric, and this allows an application to listen for connection requests across multiple domains, while active endpoint is associated to a single domain. Passive endpoints are used by connection-oriented protocols to listen for incoming connection requests by using the listen call, which is a pretty familiar call associated with TCP sockets. So passive endpoints are associated with event queues because event queues report connection requests from peers. And a passive endpoint must be bound to an event queue before calling listen. This just ensures that connection requests can be reported to the application. On the other hand, the active endpoint is used to perform data transfer operations. In basic configurations, an active endpoint has transmit and receive queues. So operations that generate traffic on the fabric are posted to the transmit queue, and operations that post buffers for receiving incoming data are submitted to the receive queue. Active endpoints can be connectionless or connection oriented, and they can also provide data reliability services. So an active endpoint is created in a disabled state, and they have to be enabled before initiating any data transfer processes. So FI passive EP call is used to open a passive endpoint, and FI endpoint call is used to open an active endpoint. Now, before an endpoint can be used for data transfers, it must be associated or bound with other resources. And the type of objects that must be bound with an endpoint depend on the endpoint type and its configuration. Resource bindings must be done prior to enabling an endpoint. So endpoints can be bound to resources along with flags. And these are some of the flags that can be set. So for example, the FI send and FI receive flags can be set while binding a completion queue to an endpoint to track any sends and receives that come in or out of that endpoint. An endpoint must be enabled before it may be used to perform data transfer. So FI enable call simply enables the endpoint passed into it. And enabling an endpoint typically results in hardware resources being assigned to it, and endpoints making use of completion queues, counters, event queues, or address vectors must be bound to them before being enabled. Okay, so a primary goal of address vectors is to allow applications to communicate with multiple peers while minimizing the amount of data needed to store peer addressing information. So conceptually, an address vector converts an endpoint address into a fabric address, fabric interface address. And address vectors are associated with the domains, as it can be seen in the figure. There are two types of address vectors. The type specifies how an application views data stored in the address vector, including how it can be processed or accessed. So the two types of address vectors are map and table. With table type of address vector, addresses are inserted into the AV and are returned as simple indices, and it can be thought of as an array of addresses. The advantage of FI AV table type is that applications can refer to peers using a simple index, eliminating the need to store any addressing data. This type maps well with applications such as MPI, where a peer is referenced by its rank. The second type is FI AV map, and applications that use a map type are required to provide the correct native fabric address for a given peer when issuing a data transfer operation. So the advantage of FI AV map is that a provider can use the FI adder T struct to encode the target's address, which avoids retrieving the data from memory. So FI AV open is used to open address vectors of both the types, and FI AV insert is used to insert address vectors of both the types. And the number of addresses is specified through the count parameter. So here is an example of how addresses look like in FI AV table and FI AV map. So both images give an example of how portable addresses like user addresses, which here is a combination of IP address and a port number, are mapped into fabric addresses by the address vector. So in that case of table, the addresses are stored using indexing system, and each fabric address is stored along with an index. While in the map type, the FI adder type of address is stored, which can directly be used by the application. So event queues are used to collect and report the completion of asynchronous operations and events. Event queues handle control services or control services events, which are not directly associated with data transfer operations. FI EQ open is used to open an event queue, and a very simple type of event queue merely tracks completed operations. As data is received or a send completes, an entry is written into the event queue. They are associated with memory registration, address vectors, connection management, or fabric and domain level events. Now, once the event queue has been created, we need to start reading for any events coming in. So we have two types of APIs for reading from event queues. The first call is FIEQ read, which is a non-blocking call. It is used to collect and report the completion of asynchronous operations and events. The format of the event data is based on type of event retrieved from the EQ. So the type of events can be control operations or connection and error notifications. Of course, all of these event types are asynchronous. Okay, on success, FIEQ read returns the number of bytes read from the event queue. The next call is FIEQ-S read, which is a blocking read call or used for synchronous operations or event types. It behaves in a similar way to the non-blocking call, with the exception that the calls will not return until either an event has been read from the EQ or an error or timeout notification occurs. Okay, completion queue is a mechanism by which an application can be notified that any data transfer operation has completed. So completion queues are associated with a resource domain as shown in the image, and they are often mapped to provider hardware mechanisms. Unlike any other objects discussed so far, completion queues are not part of the FI get info call or FI info structure. So opening a completion queue is a pretty simple call with FICQ open, and the properties and behavior of a completion queue are defined by the FICQ attribute structure. Generally, an application can choose how much data it wants to report along with the completion. So this limits the number of bytes that the provider writes into memory and also allows for completion data to fit into a compact structure. This can be done by specifying one of the CQ formats during the CQ open call. And there are 5 choices. So unspecified, context, message, data, and tagged. Now, to read all of the completion details, there is a straightforward FICQ read call, which is again a non-blocking call. And completions are written into the buff parameter, and the count parameter indicates the number of CQ entries. Next, we move on to the memory registration calls. So memory registration is the security mechanism used to grant a peer or a remote peer access to local memory buffers. A memory buffer must be registered with a resource domain before it can be used as a target of remote data transfer operations. So FIMR reg call is used to register a buffer, and by default, memory regions are associated with a domain. So a memory region that is accessible by any endpoint. A memory region is accessible by any endpoint that is associated with that domain. And a region starts at the address specified by buff, and it is len bytes long. And the access parameter are just permission flags that indicate which type of remote operations may be invoked against the region. The offset is just a number of bytes from the base address of buff. And the requested key is basically the key requested by application from the provider. If no key is requested, provider will provide a key by itself. So memory region, MR is the memory region over here, and context is user specified context that was provided along with the memory region. Next, the FIMR descriptor call will return a memory descriptor associated with the buffer that we just registered. So memory descriptors often map to hardware specific indices or keys associated with the memory region. The local key is referred to as a memory descriptor, and it may be retrieved by calling the FIMR disk call, and it can be passed directly into any data transfer operations. Now, after a memory buffer or any region has been registered, that registration request, including the buffer's address, its length, and all the access permissions, are given a registration key. And peers that issue remote memory access operations against that memory buffer must provide this key as part of their operation. This helps in protecting the unintentional accesses to that region. So the API is designed to handle MR keys that are at most 64 bits long, and the size of the actual key is reported as a domain attribute. Typical sizes are either 32 or 64 bits long, depending on the underlying fabric. So this sums up all of the basic APIs under Libfabric. And now I will go over 3 examples. The first one will be a simple messaging application with reliable datagram endpoints. Next, I would add tag matching capabilities to the application. So with this example, I want to demonstrate that how tagged messages will always be received in the same order as they were sent. And in the last example, I will add memory registration capabilities and remote memory access capabilities. So I want to demonstrate 2 operations here. One is remote memory read and the other is remote memory write. So I want to show a flow of how a simple messaging application can be created. So as emphasized before, every application starts with the FI get info call, and this call will query Libfabric and will return all of the appropriate providers. And all the applicable providers will be returned as a list of FI info structs. So since the first FI info should be most appropriate, we will select that one. Next, we initialize our fabric and the domain associated with the fabric. Next would be an endpoint, and the endpoint will be requested in FI get info. After endpoint, we will initialize our completion queue. So for example, for this example, we can assume that all the same CQ will track all of the sends and receive events. And after creating the CQ, we have to bind it to our endpoint to track any sends or receives coming in or out of that endpoint. After that, we will initialize the address vector. So we will assume that this is an indexing based table address vector, and this address vector also needs to be bound to the endpoint. So after all of the resources have been initialized, we will go ahead and enable the endpoint to send and receive data. The server will now post a receive buffer, and we will be waiting for the client to send a message. So the server will know when a message is available, when a completion is reported in the completion queue, and hence it will be reading the completion queue using FICQ read call. Meanwhile, the client will send a message with FI send call and wait for the server to get that message. When the server will get that message, it will report receive completion to the CQ, and the client will be able to read that completion using FICQ read call again. And once this exchange is complete, all of the resources can be deallocated and all the memory is freed using individual FI close calls. So this is how a small messaging application works. Now we can see this in a live example. And this is a simple diagram depicting the data transfer that we will see in this example. So using reliable datagram endpoint, we can send and receive messages. And in this example, we will just be sending one message from the client to the server. So let me switch to the example window. Okay. So this is the RDM example. We will start with the main, and this is FI alloc info call. So with FI alloc info, we ask from the provider what all services or resources we want to receive from the provider. And the destination address is just the server's address. And since this is a reliable,
Julie, I think you are not at the right part of the code, I think. Where you are on the main? Sorry to interrupt.
Oh, okay. Yeah, I'm in the main function.
Yeah, it looks like you're looking at the copyright at the top of the file.
Yeah. So I just see the example audience.c, and we are at the top of the screen. I mean, at the top of the code with the copyright information.
Let me stop and reshare.
Okay.
Okay. So
Now
I
it
think
is.
this is fine now.
Yeah, it's fine.
Yep, looks good.
Okay, so this is the main function, and we will allocate all of the resources with the fi alloc info call. And this is a destination address, which is the server's address. And we will request for RDM endpoint type, since this is a reliable datagram messaging application. And we will request for FI message capabilities. So since we are doing just a simple messaging send and receive, we will just request for the simple message capabilities. And this is a TCP provider application. So we are requesting for the TCP provider. So FI sock adder in is just the IPv4 addresses. And that's why we are requesting this addressing format here. And FI delivery complete is used to let the client know to not exit before any completions are received or before the message is sent to the server. Otherwise, the client will just exit before even the messages reach to the server. So after this, we will go ahead and initialize all of our resources. So here the first call is FI get info. So we want to so this is a destination address, that is the server's address and port number. And we are just specifying FI source flag over here to let the entity know that this is the source addresses. And the data that we will get from the provider or whichever fabrics are available, it will be received in this info struct. And the first info, so it is a linked list of all of the structs, and the first one is the one that we will select. And this is the simple TCP call to just like format the server's address into a string so that our client can use it in its command line call. And after FI get info, we do the fabric call. So FI fabric, then we open up the domain and associate it to the fabric. And then we open up endpoint and associate to the domain. And then we open up a completion queue. So the size of completion queue is going to be 128. And I talked about different formats that you can specify while opening a completion queue. So this is a messaging application. So we are just requesting FICQ format message. And in this type, we will just get the completion data along with the message data. So after that, we open up our completion queue with FICQ open, and we bind it to our endpoint. And then we go ahead and open up our address vector. So we are going to use the FI table type of address vector, and this is the count. So we are only going to add one address into the address vector. So that's why the count is 1 over here. Then you go ahead and open the address vector, and the FI AV insert call here is only done for the client. And that is because only the client is going to send to the server. So that's why we only insert the server's address into the client's address vector. And that is the FI adder over here. So after this, we bind our address vector to the endpoint with FIP bind. And the last thing is to enable our endpoint. So once all of the initialization is done, we can go ahead and run the application. So for the server, it will open up saying that it has posted a buffer and it is waiting for a message from the client. So the post receive section over here will do the FI receive call. With this call, we are, or the server is just saying that I want the message from this endpoint EP inside the buff and with this address, FI adder. Now, remember that we did not add any addresses to the server's address vector. So this basically is saying that it can receive messages from any address or any client. And here the E again is, it's basically saying that any of the entity or the resource is not available or it's not opened yet. So it should just try again later. And to just drive progress, we use the FICQ read call over here. So with this call, the server will now go into wait CQ, and since it has posted a buffer, it is now waiting for a completion in its completion queue. So with FICQ read, we read the completion queue for any completions. And once it gets the FI receive completion, it will just say, I received a message. But before this happens, we will start a client, and that client will do a post send. So inside this post send, we are doing the FI send call. So the client is going to say that I want to send my message out of this endpoint. Then the message is inside buff. So we are just printing or copying the message inside buff over here. And it is going to send at this FI adder address. So we inserted the server's address inside address vector of client, and this is that address. And FI again is just that if something is not ready yet to send the message, it is just going to say that try again later, and we'll use FICQ read in that case to just write progress. So once that is done, the client will also wait inside wait CQ, and it will read its completion queue for send completions. So once its message is sent, it will get FI send flag with its completion, and it will say that my message got sent. So after that, we are done with run, and next we'll go to cleanup. So in cleanup, as I mentioned before, we will just deallocate all of our resources with FI close call. And notice here that we opened up the fabric first, then the domain, then endpoint, then completion queue and address vector. But here we are deallocating the resources in reverse order. And that is just to make sure that no message is left hanging in between while any of the resource is closed. So if you want to close the endpoint first, that just means that the endpoint is now closed and you cannot send or receive any messages. So the first thing we do is close the endpoint, then address vector, then completion queue, then domain, and then fabric. And the last thing we do is free the info struct that we had with FI free info call. So once this is done, we are done with this example, and I here have a terminal running, so I can show this example live. So here our server has started with this address, and it has posted a receive buffer, and it is waiting for a message from the client. So on this side, we will start up a client and provide this address as its okay. So the client said that it is going to send a message to the server, and in the backend, it has opened up its sending buffer, and it has done the FI send call, and then it said my message got sent when it received its FI send completion. And on the server side, it says it received a message when it got the message and the FI received completion, and it also prints the message that this is the message I received. So this is basically a simple RDM messaging application. Now I will have to stop sharing because I again have to share the presentation. Okay. So are you able to see my presentation now?
I see it.
Okay, thanks. Right, so I just recorded a video of that example running just for if later anybody wants to see it. So this is that video, and I will skip that part. And now we move on to the tagged messaging application. So I want to show how a tagged messaging application API flow looks like. So with this example, I also want to demonstrate that how a tagged message work and specifically how the messages are received in the same order that they were sent. So all of the initialization calls will be the same from FI get info until we enable our endpoint. It's going to be the same initialization. Now, here I will be sending two messages with different tags. So the first message will be associated with tag 1 and the next message with tag 2. So the server will post two buffers for these two messages with the FIT receive call. And note that it was FI receive call in the previous example, but this time it is FIT receive because we are doing a tagged operation. So the T in FIT receive tells us that this is a tagged operation. So now the server will post buffer associated with tag 2 first and then tag 1. And the point of this example is to show that even though the server opened these buffers in reverse order, like it opened tag 2 and then tag 1 buffer, it will always receive the message associated with tag 1 first and then tag 2. So the client will send messages in tag 1 and then tag 2 format, and it will receive the message in that way. Okay, so after posting the receive buffers, the server will wait for completion and read the CQ with FICQ read call. And the client will send both the messages with FIT send call and then wait for a send completion. And after all the data transfer is done, we will close all the resources with FI close, with the FI close call. So this is just a simple animation of the tagged messaging application. And again, the tagged messages will always be received in the order that they were sent. So the client is going to send tag 1 first, and the server is going to going to receive that. And then the client will send tag 2, and the server will receive that. But if you notice here, the server has opened up tag 2 buffer first and then tag 1. So I will go ahead and show the example. Okay, so this is the main function. Is it visible?
Yeah, Julie, it's visible.
Okay, good, thanks. So this is the main function, and it is similar to the previous one. So with FI alloc info, we just allocate all of the resources or ask for all of the resources that we want for this example. And this is the server's address. And the endpoint is also same, reliable datagram endpoint. But here the FI tag capability is being asked. So in previous example, we asked for FI message, and this is because we want to use the tagging or the tag matching capability. So we have asked for the tag capabilities. And FI delivery complete is just going to tell the client to not exit before the server has received its message. The provider is same, TCP. And this time we are just doing an out-of-band addressing. So this is the out-of-band addressing. And we are only doing it because we want to use the servers like not use the server's address, but just use like any address that is any server and just say the name of that server inside the client command line call. So this process can also be done with OFI calls or Libfabric calls, but that is out of scope of this example, and we are just using basic socket TCP socket calls over here. So after the init out of band is done, we initialize our OFI resources. So here the FI get info call is first, and all of the fabric related information will be inside this info, and we will initialize the the fabric with FI info call and use the first fabric that was returned to us, and then the FI domain call and associate the domain with our fabric, and then initialize the endpoint and associate it with the domain. And the CQ size is again 128 over here. And this time we are asking for FICQ format tag. So last time it was FICQ format message because we only wanted the completion flags and the message data with our completion. But this time we also want the tag along with the completion. So we are asking for the tag format. And then we open up our completion queue with FICQ open and bind it to the endpoint. Then open up a address vector with FIAV table, and the count is 1 over here because again we only want to add one address to the address vector. And FIAV open is used to just open the call, and we open it associated with the domain, and then we bind that address vector to the endpoint and then enable the endpoint. Now, because this was out of band addressing, we have to exchange these addresses. So the server and client has to do some address exchange. And this is where we do the address exchange. So we get the name of the endpoint over here and just send out our address to the other entity and receive the other entity's address. And then we do the FIAV insert call to insert the address that we just received into our address vector. And this is the address that we can use. So FI adder is the address that we received. And after that, we do the sync progress call. So the sync progress is just used to sync up all of the process that we just did. And we will know if everything is synced up and we're ready to send messages. So in case anything is not synced up, we just use the FICQ call to drive progress until everything is synced up. So after that, we go ahead and run the application. So in this one, the server is going to start with the same message that it has posted a buffer and it is waiting for a message from the client. And it will do that posting of the receive buffer with post receive. So here the post receive is going to use FIT receive call. As I mentioned before, this is a tagged application. So we want to use FIT receive call here. And first it is going to post a buffer for tag 2. So it will say that I want the message from this endpoint in this buffer buff2 from this address. So FI adder is the client's address, and it will also say which tag is associated with this message. So it's FI tag, and we initialize it as tag 2 over here. And the E again call is just to say that something is not yet ready. So just do it again later. And after that, it will open up or post a receive buffer for tag 1. So again, FIT receive call, this endpoint buff1, and FI adder is going to be the same because it's the same client. And this time the FI tag is tag 1. So after posting both these buffers for tag 2 and tag 1, it will go ahead and wait in wait CQ. So in wait CQ, it is just going to read the completion, and once it with FICQ read, and once it receives that completion, so the server will say I received a message with this tag. So we are also printing a tag here to see how we are going to receive, or which tag we are going to receive first. And by that time, we will have started up the client. So the client is going to do a post send, and okay, so it will do the FIT send call, which is a tagged send call. And first of all, it is going to do it for tag 1. So it will send out the message from this endpoint, and the message is present in buff1, which is over here. So this is the message associated with tag 1. And FI adder is the address of the server, and FI tag is just tag1. So after that, it will do the FI send call for tag2. So again, the same endpoint, and buff2, which is this, the message associated with tag2. And this is the FI adder, which is the server's address. So it's going to be the same. And the FI tag here this time is tag2. So after this is done, it will again go ahead and wait inside the wait CQ as shown here. So inside that, it will wait for a completion with FICQ read. It will read for completions, and once it receives the send completion, and so it will get the FI send flag along with the completion, will say my message got sent. And once our application is run and the message transfer is done, we will do the cleanup. So in cleanup, as I mentioned before, we are just going to deallocate all of the resources. And it's the same here as well. So we first close up the endpoint, then the address vector, then the completion queue, then domain, and then fabric. And the last thing we do is just free the info struct. So I can now go ahead and run this application. So my server is running on the left side now. And because it was an out of band application, I can just use the server's name here. Okay. So the server has posted a buffer and it's waiting for a message. And on this side, the client is ready to send its message to this server. And here we can see that it posted the message for tag1 first and then tag2. And on the receive side, we had posted receive buffers for tag2 first and then tag1. But we received the message associated with tag1 first and then tag2. So this is what I wanted to demonstrate with the tag messaging. And here we are just printing out the message that we received. So after this, let me switch back to the presentation. And this is again the video of that example that I just ran.
Oh, yeah.
Okay. So so next I want to demonstrate the Rma application, and this is also going to be a reliable datagram application, but with remote memory access capabilities. So like all the other examples, the Rma application also begins with FI get info call, and all the initialization is going to be the same until we reach FI enable. So domain, so fabric, then domain, then endpoint, then completion queue, bind it to the endpoint, address vector, bind it to the endpoint, enable the endpoint. And after enabling the endpoint, we will create memory regions and then register them. So now with this example, I want to show two operations. One is remote write, and one is remote read. So in the remote write example, the client is going to write data from its local write buffer to the server's write buffer. So here the server's buffer is going to be remote for the client. And hence we can say that this is a remote memory access or remote memory write application, because the client is remotely writing data into the server's memory or to a remote memory, that it's a remote memory for the client. And in the remote read operation, the server is going to read data from client's read buffer into its own local read buffer. So here we can say that the server is accessing data from a remote location and copying it into its own local buffer. So in total, we will need 4 buffers here: client's write buffer, client's read buffer, server's write buffer, and server's read buffer. And we will register all the 4 memory regions with FIMR reg call. We will also have local descriptors for each regions with FIMR disk call, and keys to access all the memory regions with FIMR key call. So after this is done, we will write from the client's local write buffer to server's write buffer using FI write. And then we will check the completion queue for write completion. And once we have that, the client will have written data into the server's write buffer by remote memory access or RMA. And after that, we will do the read operation with FI read, where the server will read data from the client's read buffer and copy it into its own read buffer. And again, we will check the completion queue for read completion. So again, here the server will copy data from client's read buffer by doing remote memory access. So the data is always moving from the client to the server in both the read and write operations. And then we just close up all of the resources that we had assigned. So this is a small diagram to show the movement of data. In the write operation, the data is moving from the client to the server, and the client is initiating write from its local write buffer to the server's write buffer. And in the read operation, the data is again moving from the client to the server, but this time the server is initiating a read, and it's reading data from the client's read buffer to its own read buffer. So now let's see the code for this, and we'll run it. So the application starts with FI alloc info as previous applications. And we are just allocating or asking for resources with this call. And this is the server's address, destination address. The endpoint is same. It is reliable datagram. And this time we are asking for RMA capabilities with FI RMA. So last time it was tagged, and then previous to that it was FI message. And this time, since we are doing a remote memory access operation, we want to receive all the or get all the RMA capabilities from the provider. And the FI delivery complete is just for the client to not exit before server has received its data. The MR modes are or you can call it as some modes that are requested along with the memory registration, so that we can know what kind of processes or operations we want to do or are allowed with that memory buffer. So here we have 5 different modes, and we are requesting the TCP provider for this application as well. So after all of this, setting up the hints and requesting for resources, we go ahead and do the out of band initialization. It's going to be the same as before, so I'm not going into that. And the initialize call. So here, as all the previous examples, it is FI get info, which is the first call, and all the fabric information will be provided here in info. We will select the first one and open up the fabric with FI fabric. Then next domain and associate it to our fabric. Then endpoint and associate to the domain. Then completion queue. Size is 128, and we have switched back to message format because we just want the completion flags and the data along with it. There's no tag matching or anything like that here. So it's just a simple messaging format. Then we open up the completion queue with FICQ open and bind it to our endpoint. Then we open up the table type of address vector. The count is again 1 because it's just one server and one client. And open up the address vector, bind it to the endpoint, and enable the endpoint. So after this, all of this is the memory registration calls. So we will have 4 different buffers, as I mentioned before: server's read buffer, server's write buffer, client's read buffer, and client's write buffer. So we will register the reads and write buffers with FIMR reg call. So and this is mapped to the domain as well, as we saw in the figure as well. And we will request for FI read and FI remote read flags. So for this, we only need FI read and FI write. And this is the local key of that memory region. And this is the actual memory region that we have. So I have initialized this over here. FI MR read and MR read and MR write. So once we have registered these memory regions, this is the descriptor call. So this is the local descriptor or local key for MR write region and the key for MR write. And this is the descriptor for read and key for read region. And this is just the address of that. So the region will have a starting and ending address. So this is just the local address write and local address read are the addresses where our memory regions are starting from. So this is the write region's address and this is the read region's address. So after that is done, we will have to exchange all of this information. So with this, we have to exchange the addresses of the read and write memory regions and the keys associated with those regions. So with exchange info. Okay, so this is just exchanging the servers and clients' actual address. And then also send the address and receive the other entity's address and insert the address with FIAV insert. This will be the client's or server's address, depending on which one is running this application. And then this is the sends and sock send and sock receives for our key and our addresses. So with this sock send call, we are sending the local key associated with our write buffer, and we are receiving the remote key for the other entity's write buffer with this call. And similarly, this is the read key and this is the remote read key. So remote read key is the other entity's read buffer's key. And these are the addresses. So local address write, this is our address, write buffer's address or write memory region's address that we are sending. And we are receiving the remote entity's write memory region's address. And same for the read memory regions as well. And the sync progress is again to just sync up the address exchanges. So we just send and receive all of the addresses or keys and everything, and then we just do FICQ read to drive progress in case we don't have any information yet. So after the initialize is done, we go ahead and run the application. So with this, as I mentioned before, we are doing 2 operations, FI write and FI read. So in FI write, the client is going to write from its own buffer to the server's write buffer. So the data is always moving from the client to the server. So we will fill up all the buffers that we want to, all the messages that we want to send while we are starting up the client. So this is the read message and this is the write message, and we are filling up our buffers with those messages. And the client is then going to do a do write. So with do write, this is the FI write call that will be used to write from one region to another, or remotely write from one region to another. So the write is happening on this endpoint. This is the buffer that we want to write, and the local descriptor of our write buffer and the address where we want to write it. like the address of the server where we want to write it, and the remote address write. So this is the address of the write buffer or the server's write buffer where we want to write it. And we also will need the key in order to access that memory region. So this is the key for that. So with this call, we will finish up our write, and E again is where we just wait for something to, if something's not ready yet, we just wait for it, and then we do the FICQ read in order to drive progress. And once the do write is done, we go to wait CQ. So with wait CQ, we are reading for a completion with FICQ read call. And once we have done the write, we will receive the FI write completion flag along with the completion in our completion queue, and we will just end saying my write has finished. And then this is one operation. So this is the write operation, remote write, and the next operation is FI read. So the server is going to read from client's read memory region remotely and copy that message in its own read memory region. So before initializing anything, it will just sync all of the buffers and memory regions and addresses and keys. And after that, it will say that server is ready to read a message from the client. Then it will do the FI read here. So with this FI read call, it is saying that it wants to read the message from this endpoint inside this buffer, buff read. This is the local descriptor or the local key of its own read buffer. FI address is the client's address, and remote address read is the client's read memory region's address. And this is the client's read memory region's key, which will be used to access that memory region. So once this FI read is done, we will go and wait for a completion inside wait CQ. So here it will get a completion FI read completion flag along with its completion, and it will say that my read has finished. So this is the FI write and FI read call and the remote read and remote write operations. So once this is done, we will just again go ahead and clean up all of our resources. So we are closing up the memory regions first over here, then the endpoint, then address vector, completion queue, domain, and fabric. And all of this once is closed, we just go ahead and free our info struct. And now I can just go ahead and run the application. So this is our server. Okay. So the server is waiting for a message. So this is just, it's saying that it's ready to read a message from the client. And on this side, the client is ready to write to the server. So once it has finished the FI write call, it will get a write completion and will say that my write has finished. And on the server side, the server is ready to read the message. So it will read it with the FI read call. And once it has finished that read call, it will get a read completion. So FI read flag with its completion. And then it will say that my read has finished. And then we are just saying what messages the server has received, because at the end, the server is going to have both the messages, the read and write messages. So these are the messages. So this is how a simple application, like Rma application works. And this is again the recording of the same message. So if anybody wants to take a look at that later, and I will skip for that. And this is just some more information about our Libfabric, and this is the Open Fabrics org, and some tutorials are present over there. So if you want to have a look at more tutorials, you can go at this website and check for more tutorials. This is our Libfabric GitHub. So I have not put up the examples, all of these examples link here, but it's posted in the Slack channel. And if you want to build those examples and run them yourselves, you would need Libfabric along with it. So this is where you get Libfabric from. Here we have the developer's guide. So if you want to read out more about Libfabric and in more details, if you want to know, then you can read the developer's guide. And this is our man pages. So man pages has a lot of detail about different APIs. So if you want to read out those. And yeah, that brings us to the end of the tutorial. Thank you so much for attending. And for the questions part, I guess, are there any questions on the Slack?
Juhi, I think currently I'm not seeing any questions on the Slack, but we'll still be available on the Slack. And if people need some more time to digest, and then if they have any questions, they can still post it on the Slack, or they can always connect with us. Yeah, the information is there in the GitHub, and then you guys can email us.
Yeah, I thought of a couple questions, if you don't mind me asking verbally.
Sure.
Maybe it'll get folks warmed up. Can you tell me anything about doing collective operations in Libfabric? I asked the same thing with UCX. And I'm wondering to what degree it's supported, or if there are plans users should know about, and or should we really be thinking about, send, receive, and read, write with Libfabric?
So yeah, I think we do have a collective API as well on the Libfabric. I think it's available on the man pages also, and also on the developer's guide. So we do have support for it, but I think Rajalaxmi might better know if we are using it anywhere. So
I think Sean wanted to answer it, but I think I'll let him answer it on the Slack. And I think he cannot talk on the on the Zoom here.
Who? I could maybe pass the mic to someone. Oh, I see.
It's
Sean
Sean
Hefty's.
Hefty.
Oh yeah, I'm gonna allow Sean to talk if you want to say anything, Sean. Yeah, that'd be great.
Can you hear me now?
I can.
Yay, okay. Yeah, so Juee is right. So we have collective operations defined in Libfabric. There's a full set of collective calls like all reduce, barrier, broadcasts. Those are depending on how the providers implemented it, or if the provider has implementation, but there are a set of collective calls. They specifically try to target collective offload into the network. So switch-based collectives, for example, or accelerations on the NIC. We're not trying to be MPI, but those are available through the APIs.
Nice, very nice. Yeah, thanks, Sean. Yeah, no questions in Slack that I can see, but yeah, please don't be shy, and again, feel free to ask questions online. Maybe I'll just ask one more question I thought of. When you were talking about domains towards the beginning, it made me wonder if when it comes to programming multi-rail NICs in Libfabric, how does that work? Is each NIC associated with an FI domain, or is there something else exposing that in the API? Because I feel like I've seen multi-rail is supported, right?
So I think multi-rail support was there, but it's not there anymore. I guess Sean can comment on
Oh.
that again.
Can I
Oh.
still talk?
Yes.
Oh, okay. Yeah, so the domain object is abstract. It can be tied to a specific NIC. And part of the FI info structure, if the domain is tied to a NIC, you can get NIC attributes from it, but it's not a requirement. So if you have the case where with multi-rail, the domain is not tied to a specific NIC, you would not get NIC attributes, and the domain would actually map across possibly 2 or 3 different NICs. And that's kind of how the multi-rail is enabled. And it doesn't even have to be the same type of NICs, right? You could map across Ethernet and InfiniBand if it made sense, but the multi-rail would be more generic, and the domain doesn't have to have a NIC. Like the shared memory domain is not tied to a NIC, for example. It's just kind of a boundary for how those resources are shared.
Nice. Yeah, good to know. Thank you. Thanks for clarifying. Yeah, again, we got a thanks for a great presentation. Yeah, it was a great tutorial. I love the progression of send receive to tag send receive to FI read write. Those are great examples. And yeah, feel free to post questions in Slack. And if there are no other questions there, I think we could wrap up. In fact, it might help a bit. We've been having technical issues going from session to session, and we could use a few minutes to prepare for the next one.
Yeah, I would like to just acknowledge, thanks to Sean. He's the architect.
Yeah.
Fabric.
Right.
Thanks for jumping in
Yeah.
here. Yeah.
I'm glad I was able to pass him the mic.
Thank you all.
Okay, thank you.
Should we just
Thank you.
end the session here? Or,
Yep, I think I will end the session and it'll stop the recording, and I'll see you all in the next one where we're going to change subject completely and talk about microservices.
Thank you.
All right, have a good one.
Thank you.
Bye now.